Hello, everybody. So, after having studied the principle of pre-stressing, the methods of pre-stressing, and the necessity of pre-stressing, now we uh, take up the next part, that is analysis of PSC sections for Flexure. Now, what we have understood is that pre-stressing is transferring a pre-compression to a beam or a flexural member, and this pre-compression is applied so as to nullify the effect of the external forces, that is to counter the tensile stresses. So with this idea, uh, so before we tell you what is analysis, now in pre-stressed members, when we mean say analysis, it generally means obtaining the stress values in a member at different stages or phases. And for doing this analysis, we have certain assumptions which are very much similar to those in pure bending, that the sections remain plane uh, before and after bending. There is perfect bond between concrete and prestressing steel, and both concrete and steel, the stresses are within the elastic limit. And as I told you, uh, the analysis, there are different approaches of doing carrying out the analysis of a PSC member, and they are broadly uh, three concepts. What we identify as the stress concept, force concept, also called as the internal resisting couple concept, and lastly the load balancing concept. And as we understand, analysis means obtaining the stresses at different stages. Now before we take up, so we will discuss these three concepts and their applications. So first, the stress concept. Before we take up the stress concept, we shall recollect what we have discussed in stresses in beams in the subject strength of materials. So to determine the stresses in a beam uh, using the theory of pure bending. So when it is required to find out the stresses in a beam, so we have this theory of pure bending. A beam subjected to load, here a simply supported beam, will bend, resulting in compressive stresses in the upper fibers and tensile stresses in the bottom fibers. And now it is required to find out the stresses at a particular section, and in a particular fiber. So the fiber shown here on the cross section is at a distance y from the neutral layer or neutral axis, and the stress distribution is according to the assumptions is shown here, and the stress in this particular fiber can be obtained using the equation of pure bending. So using the first two ratios here with usual notations, so the bending stress in this particular fiber is given by this expression. M is the bending moment at the section, I is the moment of inertia of the cross section about the neutral axis or centroidal axis, and y is the distance of the fiber from the centroidal axis. Now we know that the stresses are maximum at the outermost fibers, the top and bottommost fibers, and these stresses can be obtained by substituting the corresponding distances. So accordingly, we have these expressions for the stress in the top and bottom fiber. So here YT and YB are the fiber distances, and since YT and YB are constants for a cross section, this I upon Y, the ratio, is replaced by a sectional property, what we call as section modulus. Hence the stress in the extreme fibers, what we remember, is given by M upon Z. So with this background of obtaining the stresses in a beam, now we can move into understanding the stress concept. So in this stress concept, which was developed by uh, Frisinet, so a PSC beam is considered here, and the pre-stress is considered as a force in addition to the external force. So here the member, the beam is assumed to be subjected to a two system of forces. One is the pre-stressing force and the other one is the external load, and the stresses are obtained for these two force systems. So to understand this stress concept, we will consider a PSC beam simply supported, subjected to a straight eccentric cable and having a cross section. It could be any symmetric cross section, and the load acting on the beam can be considered as a dead load and live load. The dead load would include the self weight, and it is required to obtain the stresses at a particular cross section. Now drawing the free body diagram of this beam, when we consider the pre-stress as a force, we remove the cable and replace it by an external force acting at an eccentricity. And further, the free body diagram can be simplified, showing the pre-stressing force acting at the center, accompanied by a moment of or couple of magnitude P into E, E being the eccentricity. Now, the forces at the section where the stresses are to be determined are shown here. So at the section XX, we have this concentric force, pre-stress force P acting, and the moment due to the eccentricity, and the moments due to the loads, which are shown as MD and ML respectively for dead and live loads. So it is required to obtain the stresses at this particular section XX, this being the cross section, due to these various forces acting. So it is the same section shown here. The forces acting on the cross section and their effect can be considered one by one independently. So first, the pre-stressing force acting at the center will induce uniform compressive stress. We use positive sign for the compressive stress, and the moment due to the pre-stressing force will induce bending stresses. Since the moment is hogging in nature, so as we see here, the moment is hogging, so this induces tensile stress in the top fibers and compressive stress in the bottom fibers, and these stresses, as we have understood, is given by M upon Z, M is the moment, and the moment is due to the eccentricity of the prestress, which is P into E. So this is the stresses due to prestress. One due to the concentric force, and due to the eccentricity of the prestressing force. Now the stresses due to the dead load. So knowing the dead load moment, the stresses in the top and bottom fiber are given by M upon Z, and we know that the moment being sagging, the stresses is compressive in the top fiber and tensile in the bottom fibers. Similarly, the live load stresses at the cross section can be shown like this. Now this is the stresses due to all the forces acting at the cross section. The net or the resultant force on the cross section can be obtained by superimposing or taking an algebraic summation of all these forces. So the force, the stress in the top fiber is given by this expression, which happens to be the summation of superpositioning of all these forces. And as we see here, due to the prestressing force, this is compression at the top fiber. Due to the eccentricity, it is tensile stress, and due to the loads, it is compression. Similarly, at the bottom fiber, we have this stress expression, and these are the general stress expressions which we will have to remember for analyzing a PSC member by this stress concept method. Now, when we come to analysis of a PSC section, we know that there are two distinct stages in a PSC member, and these two stages is what we call as the initial stage and the working stage. So the initial stage, or the transfer stage, what we call, so this is the stage where we have the initial prestressing force applied to the member, and at this time only the dead load is acting on the member, and the resultant stresses at any section is given by these expressions which we had just now obtained. So this is the stress state at transfer stage. Now when we go to the working stage or the final stage, so the forces acting on the member, the prestressing force is now the final prestressing force, which is after undergoing all losses. And now in addition to dead load, the live load acting on the member is also to be considered. So the forces acting are final prestressing force, dead loads, and live load. And the resulting stresses at any fiber, at any section, at any section are given by these expressions. So here PF is the final prestressing force, which is after all losses. If Pi is the initial prestressing force, nu is the loss ratio, then we have PF is equal to nu into Pi. Usually the loss ratio is between 0.8 to 0.85. So using the expressions for calculating stresses at transfer and the stresses at working stage, so we will be able to carry out the analysis of PAC sections. So now we take up numerical examples, and when we take up the numerical examples, so depending on the data given and what is required, we can put the problem types as three distinct types. So the first type being where we are given information about the beam and we are asked the resultant stresses. The stresses may be at transfer stage or final stage or both. And the second type of problems is where we are given the data, the information about the beam, the span, the support condition and the load. And in addition, we are given the stress values, the stress condition at transfer or final. With this data, we may be asked to find out the prestressing force and its eccentricity or both of those. And the third type is where we are given the data regarding the beam and also the prestressing force and its eccentricity, and it is required to find out the load acting on the beam. So all these three types of problems can be solved using the stress conditions or the stress equations which we have just now derived. So we'll take up the numerical examples. So here this is the first example where we have an unsymmetrical beam. So it has to support and superimpose load of 2 kilonewton per meter over a span of 8 meters, and the cross section of the beam is an I section having a top flange 300 mm wide into 60 mm thick, bottom flange 100 mm wide into 60 mm thick. The web is 80 mm thick. Overall depth of the section is 400 mm, and at mid-span the effective prestressing force is 100 kilonewton, which is located at 50 mm from the soffit of the beam. Soffit meaning bottom of the beam. And we are required to estimate the stresses at the mid-span of the beam for the following conditions, that is pre-stress plus self-weight and pre-stress plus self-weight plus live load. Now the first condition is what we call the transfer stage, and the second condition is what we call as the final or working stage. So the given data can be summarized like this. So the span, load, the prestressing force, and here the concrete density is not given, which is required to calculate the self weight. It can be assumed as 24 kilonewton per meter cube. So this is a problem where information about the beam is given and it is required to find out the stresses. So before we proceed, we once again look at the formulations. So to find out the stresses at transfer and final stage, so we need all these values. So we need the information, the details of the cross section. We need to calculate the moments. So we will solve the problems stepwise. So our first step will be to obtain the properties of the cross section. So based on the description, the given cross section is an I section, and the properties of the cross section are obtained. So the area of the cross section and the centroidal axis has to be located. So this is done by applying the first theorem uh, of the moment of areas, and this gives us YB, that is the location of the centroidal axis from the base or the bottom reference, and accordingly we get the distance to the topmost fiber, and hence we can get the eccentricity. So the cable is located at a distance of 50 mm from the soffit, from the bottom. Hence we can get the eccentricity, which is the distance from the centroidal axis to the cable. Next is obtaining the moment of inertia of the cross section about the centroidal axis. Since the cross section is an unsymmetrical section, so we need to apply parallel axis theorem. Now these calculations, the details will not be covered here, since locating the centroid moment of inertia has been discussed earlier. So by parallel axis theorem, we get the moment of inertia of the cross section about the centroidal axis, and so this is after getting this, we get the section modulus, so which is ZT and ZB. So with this sectional properties, the other the next calculation will be to obtain the dead load and live load bending moments. And since the maximum stresses are to be determined, which will occur at the section of maximum moment, so these calculations will be done at mid-span section. So at the mid-span section, the moments will be calculated. To calculate the dead load moment, we need the self weight of the beam. So the self weight of the beam is given by cross-sectional area into density. So the density of concrete is assumed as 24. That gives the self weight as 1.12 kilonewton per meter, and the bending moment is given by WL square by 8. Similarly, the live load on the beam is specified as 2 kilonewton per meter. That gives a live load bending moment of 16 kilonewton per meter. So with this, we can now calculate the stresses. So the stresses are to be calculated at two stages. One is due to pre-stress and self-weight. So the pre-stressing force is given. So we use the expressions to calculate the maximum stresses which occur at the extreme fibers. So this is the expression for the stress at the top fiber and the expression for the stress in the bottom fiber. So here, since there is no loss in pre-stressing force, the same value of P will be used for both the stages. So the stress due to direct pre-stress, P upon A, due to the eccentricity of the pre-stress, and the stress due to the dead load, so are calculated, and these are the final stresses in the top and bottom fiber. Similarly, we can calculate the stresses due to pre-stress, self-weight and live load. So now the stresses due to live load are to be included here, and this gives us the values at the top fiber at 3.3 Newton per mm square and at the bottom fiber as 0.35 Newton per mm square. So these stresses so calculated at the two stages can be plotted. So This is the stress distribution, uh, wherein this is at the transfer stage, and this is the stress at the final stage. We will take up one more example. So the example is like this. A box girder of a PSC bridge of span 40 meter has overall dimensions of 1200 mm and 1800 mm. The uniform thickness of wall is 200 mm. The live load moment at midspan is 2000 kilonewton meter at midspan. The beam is prestressed by a parabolic cable with an effective force of 7000 kilonewton. The eccentricity at midspan is 800 mm and is concentric at supports. Compute the stresses. So here the given span is 40 meters and the live load is not given, but straight away the moment caused by the live load is given as 2000 kilonewton meter, and the pre-stressing force is given, and the cable is not straight, it is parabolic, and the eccentricity at midspan is 800 mm. Now coming to the cross section, it is a bridge girder, it is a hollow box girder. So this is the cross section. So it is a hollow box girder and the cable is parabolic. So the cable is parabolic as you see here. At the support the eccentricity is 0, we say it is concentric. At midspan it has an eccentricity which is given as 800 mm. And here again we are asked to find the stresses. So we know the process. So once again let us look at the expressions. So here we have these expressions. See the stresses at transfer and the stresses at final stage. So knowing these expressions, we can continue with the problem. So first, as usual, we will determine the cross-sectional properties. So it is a symmetric box section, hollow. So the cross-sectional area is obtained by outer rectangle and subtracting the inner rectangle, and centroidal axis, since it is symmetric, total height being 1800, the centroidal axis is located, so YB is equal to YT is equal to 900 mm, and the moment of inertia about the centroidal axis is obtained by subtracting mi of the outer area, subtracting the mi of the inner rectangle from the outer rectangle, so we get the moment of inertia, and the section modulus top and bottom are equal given by this expression. So now to calculate the stresses, so here again as per the given data we will calculate the final stresses, for which we need the self weight. So the self weight is cross sectional area into concrete density, so we get the self weight of the beam as 24.96 kilonewton per meter, and at midspan when we calculate the bending moment by WL square by 8, so we get the bending moment due to the dead load, and there is no need to calculate live load bending moment. The live load bending moment value is given. So using these two moment values, we can calculate the stress in the top and bottom fiber using the expressions, and we get the stress values as plus 9.86 in the top fiber and plus 3.6 in the bottom fiber.